Think about that. You, sitting there watching this video, are currently screaming through the void faster than anything humans have ever built. Your chair, your room, your entire city, rocketing through darkness at speeds that would shatter anything in its path. And yet, your coffee sits perfectly still on your desk. This is just the beginning of how strange the universe really is. Today, we're going to answer two questions that have haunted humanity since we first looked up at the stars. How big is the universe? And does it actually end? What we're about to discover will break your brain in the best possible way. Because the truth, the real truth about the size of the cosmos is so much weirder than anyone told you in school. We're going to start small, with things you can actually picture in your mind. Then we'll zoom out, step by impossible step, until we reach scales so massive that the numbers themselves start to fall apart. And at the very end, we'll tackle the ultimate question. The edge. Does space just stop somewhere? Is there a wall, a boundary, or does it go on forever? Spoiler alert, the answer is going to mess with your head. Let's start with that 1.3 million miles per hour thing, because most people have no idea this is happening. You know Earth spins, right? That's basic stuff. We rotate once every 24 hours, which means if you're standing at the equator, you're moving at about 1,000 miles per hour. That's faster than the speed of sound. You're already breaking the sound barrier just by standing still. But Earth isn't just spinning. It's also orbiting the sun at 67,000 miles per hour. Picture a race car going 200 miles per hour. Now imagine something going 335 times faster. That's you, right now, circling the sun. But wait, it gets crazier. Our sun isn't sitting still either. It's dragging us along as it orbits the center of the Milky Way galaxy at 514,000 miles per hour. We're on a 225 million year joyride around a supermassive black hole, and we're only about halfway through our current lap. And the Milky Way itself? It's moving through space at 1.3 million miles per hour, pulled by gravity towards something mysterious that we'll talk about later. All of this motion, stacked on top of each other like cosmic Russian dolls. And you feel none of it, because everything around you is moving at the exact same speed. Your entire frame of reference is in motion together. This is our first hint that space is much stranger than it appears. Now, before we start our journey outward, we need to talk about the universal speed limit, light. Light moves at 186,282 miles per second, not per hour, per second. That's fast enough to circle Earth 7.5 times in a single second. It's the fastest thing that exists. Nothing can go faster. Not spacecraft, not radio waves, not even information itself. And here's the wild part. This speed limit is the only reason we can see the universe at all. When you look at something, you're not seeing it as it is right now. You're seeing it as it was when the light left it. Look at your hand. You're seeing it as it was 0.000001 seconds ago. Look across the room. You're seeing that wall as it existed a few billionths of a second in the past. This barely matters in everyday life. But once we start talking about space, this time delay becomes everything. The moon is 238,855 miles away. Light from the moon takes 1.3 seconds to reach your eyes. When you look at the moon, you're literally seeing 1.3 seconds into the past. That doesn't sound like much, but now think about this. Every photo of an astronaut on the moon was taken 1.3 light seconds away from Earth. When Neil Armstrong said, "One small step for man," people listening on Earth heard it 1.3 seconds after he actually said it. Not because of radio delays, but because of the universe itself. The sun is 93 million miles away. Light from the sun takes 8 minutes and 20 seconds to reach us. This means if the sun suddenly exploded, right now, this exact second, we wouldn't know for 8 minutes and 20 seconds. We'd keep seeing sunlight, feeling warmth, completely unaware that our star had just died. For 8 minutes and 20 seconds, we'd be living in a doomed solar system without knowing it. Mars, depending on where it is in its orbit, is between 4 and 24 light minutes away. When we send commands to rovers on Mars, there's a delay. We tell Perseverance to turn left, and 20 minutes later, we get confirmation that it turned left. By the time we see what the rover is doing, it's already ancient history. Jupiter, 40 light minutes away. Saturn, 80. These planets are so far that when you see them through a telescope, you're seeing them as they were over an hour ago. And Neptune, the most distant planet in our solar system, is 4 light hours away. 4 hours. Imagine sending a text message to Neptune. You hit send, and 4 hours later, they receive it. 4 hours after that, you get their reply. An 8-hour conversation lag. But here's what's absolutely insane. Neptune is basically next door compared to what comes next. In 1977, NASA launched 2 spacecraft called Voyager 1 and Voyager 2. Their mission was to explore the outer solar system and then just keep going. Forever. Voyager 1 is now 15 billion miles from Earth. It's been traveling for over 45 years, moving at 38,000 miles per hour, and it's barely made a dent in the cosmic distance scale. Here's the reality check. Voyager 1 won't reach another star for 40,000 years. Let that sink in. The furthest object humans have ever sent into space, traveling for nearly half a century at speeds we can barely comprehend, won't reach the next star system until the year 42,000 AD. And that star, it's not even close to the nearest star. The nearest star to us is Proxima Centauri, 4.24 light-years away. Voyager would take 73,000 years to get there. This is where our brains start to break, because a light-year isn't a measurement of time. It's a measurement of distance. 1 light-year equals 5.88 trillion miles, the distance light travels in 1 year. Proxima Centauri is 4.24 light-years away, which means it's 24.9 trillion miles from us. If you could drive there in your car at 60 miles per hour, never stopping, it would take you 47 million years. And Proxima Centauri is our nearest neighbor. Our Milky Way galaxy contains somewhere between 100 and 400 billion stars. Most estimates put it around 200 billion. That's 200 billion stars, each one potentially surrounded by planets. The galaxy is 100,000 light-years across. That means light, traveling at 186,282 miles per second, takes 100,000 years to cross from one side to the other. Here's a thought experiment that shows how empty space really is. If you shrunk the Milky Way down so that our solar system was the size of a quarter, the nearest star would be another quarter sitting 370 miles away. The galaxy would stretch across the entire United States, and most of it would be completely empty. We think of space as being full of stars, but it's not. It's mostly nothing. Vast, cold, empty nothing, with occasional tiny dots of light separated by incomprehensible distances. Our sun sits about 26,000 light-years from the center of the galaxy. We're in a quiet suburban arm called the Orion Spur, slowly orbiting a supermassive black hole that weighs 4 million times more than our sun. It takes our solar system 225 million years to complete one orbit around the galactic center. The last time we were in this position, dinosaurs had just started to evolve. The next time we come back around to this spot, who knows what Earth will look like, if it's even still here. In 1990, Voyager 1 was 3.7 billion miles from Earth, about to leave the solar system forever. Scientist Carl Sagan convinced NASA to turn the spacecraft's camera around for one last look at home. In that photo, Earth appears as a single pixel, a pale blue dot, barely visible against the darkness. That tiny speck contains every human who has ever lived. Every war, every love story, every discovery, every triumph and tragedy in human history, all compressed into a dot smaller than a grain of sand. Sagan wrote, "Everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on that mote of dust suspended in a sunbeam. From just the edge of our solar system, we're already invisible, a speck, a rounding error in the cosmic calculation. And we haven't even left our neighborhood yet. This is where things start to get truly strange. Because everything we've talked about so far, our entire solar system, all the planets, the sun, the distance Voyager has traveled, all of it fits inside a sphere about 0.001 light years across. The next star is 4.24 light years away. We're about to take a step into a scale that humans were never meant to comprehend. And once we do, there's no going back to thinking of ourselves as anything other than impossibly, cosmically small. Are you ready? Imagine you're on a spacecraft leaving Earth. You watch the moon shrink behind you. Mars becomes a distant red dot. Jupiter's massive bulk fades into darkness. You pass Neptune, the edge of our planetary neighborhood, and then nothing.
For years, you see nothing. Just darkness and distant stars that don't seem to get any closer. This is interstellar space, the void between stars, and it's almost perfectly empty. 1 hydrogen atom per cubic centimeter, that's the average density of interstellar space. For comparison, the air you're breathing has about 10 billion molecules per cubic centimeter. Space isn't just empty, it's the definition of empty. You travel for a year, then 10 years, then 100 years. The stars barely move. Earth's sun has become just another point of light, no brighter than any other star you can see. This is the reality of interstellar travel. It's not an adventure. It's a prison sentence of endless darkness where nothing happens for lifetimes at a time. And this void, this nothingness, fills most of the galaxy. Alpha Centauri is actually 3 stars orbiting each other. 2 sun-like stars called Alpha Centauri A and B, and a small red dwarf called Proxima Centauri. Proxima has at least 2 planets, including one called Proxima Centauri B that sits in the habitable zone where liquid water could exist. This planet might have oceans, it might have life. It's 4.24 light years away, and we will probably never know. With current technology, getting there is basically impossible. Our fastest spacecraft, the Parker Solar Probe, reaches speeds of 430,000 miles per hour. At that speed, it would still take 6,700 years to reach Proxima Centauri. But let's imagine we could build something better. Let's say we develop a spacecraft that can travel at 10% the speed of light. That's wildly beyond our current capabilities, but let's dream big. At 10% light speed, the trip would take 42 years. But here's the problem. At that speed, a collision with something as small as a grain of sand would release the same energy as a nuclear bomb. Space isn't empty enough for safe travel at those speeds. And even if we solved that problem, even if we built a ship that could safely travel at 10% light speed, it would take 42 years to get there and another 4.24 years for any message to get back to Earth. You'd send astronauts to another star system, and by the time they arrived and radioed home to say, "We made it," nearly 50 years would have passed on Earth. Most of the mission controllers would be dead, the politicians who funded the mission would be dead, the world would have moved on. This is why interstellar travel isn't just hard, it's civilizationally hard. It requires a level of patience and long-term thinking that humans have never demonstrated. But let's zoom out and look at our stellar neighborhood. Within 30 light years of Earth, there are about 500 stars. Some are bright giants, Most are dim red dwarfs, smaller and cooler than our Sun. Many of these stars have planets. We've confirmed thousands of exoplanets just in our local region of the galaxy. Statistically, there should be billions of potentially habitable planets in the Milky Way alone. Billions of worlds where liquid water could exist, where life could emerge, where civilizations could develop. So where is everyone? This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where are they? If the galaxy is full of habitable planets, and if the galaxy is billions of years old, then intelligent life should have emerged many times over. Some civilizations should be millions of years more advanced than us. They should be everywhere. We should see evidence of them. Megastructures, radio signals, probes exploring every star system. But we see nothing. We hear nothing. The galaxy is silent. Maybe we're the first. Maybe intelligence is incredibly rare. Or maybe there's something ahead of us. Some inevitable catastrophe that wipes out every civilization before they can spread to the stars. We call this the Great Filter, and we don't know if it's behind us or in front of us. At the center of the Milky Way, 26,000 light-years from us, sits something called Sagittarius A. It's a supermassive black hole containing 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. We can't see it directly, because black holes are, well, black, but we can see stars orbiting around it at speeds up to 5,000 miles per second. These stars are being whipped around by gravity so intense that space and time themselves are warped. There's one star called S2 that orbits Sagittarius A star once every 16 years. Its closest approach brings it within 11 billion miles of the black hole, traveling at nearly 5% the speed of light. At that distance, time literally slows down. If you could somehow stand on that star, you'd age slightly slower than someone on Earth. This is Einstein's general relativity in action. Massive objects bend space-time like a bowling ball on a rubber sheet. The more massive the object, the more space-time bends. Get too close, and space-time bends so much that even light can't escape. That's what a black hole is. Not a thing, but a place where the universe breaks, where gravity becomes so intense that the normal rules stop working.
Here's something interesting. Not all parts of the galaxy are equally good for life. Too close to the galactic center, and you're in a dangerous neighborhood. Supernovae explode regularly, bathing nearby planets in deadly radiation. Stars are packed so tightly that gravitational interactions could fling planets out of their orbits. And that supermassive black hole occasionally feeds, creating jets of radiation that could sterilize anything nearby. Too far from the center, and there aren't enough heavy elements to form rocky planets. The outer regions of the galaxy are mostly hydrogen and helium left over from the Big Bang. You need carbon, oxygen, iron, all the stuff that makes planets and life possible. And that stuff only exists because earlier generations of stars created it and then exploded, scattering it into space. We're in the Goldilocks zone. Not too close, not too far. Just right for life to emerge and survive for billions of years. This might be one reason we haven't found aliens yet. Maybe most of the galaxy is just too hostile for complex life. Maybe we're in one of the few neighborhoods where evolution has time to work. If you could somehow step outside the galaxy and look at it from above, you'd see a beautiful spiral structure. 4 or 5 major arms, depending on how you count them, rotating around the galactic center like a slow-motion hurricane. These arms aren't solid, they're density waves, regions where stars and gas clouds are slightly more compressed. Stars move in and out of the arms as they orbit. Our Sun actually passes through a spiral arm about once every 100 million years. Some scientists think these passages might affect Earth. As we move through a denser region, there's a higher chance of nearby supernovae, which could impact our climate or cause mass extinctions. It's controversial and the evidence is unclear, but it's possible that our position in the galaxy has influenced the evolution of life on Earth. The galaxy is about 1,000 light-years thick at our location. We're sitting about halfway up in the galactic plane. Above and below us, the density of stars drops off rapidly until there's nothing but empty space and a few stray globular clusters, ancient balls of stars that orbit the galaxy like bees around a hive. Here's where things get really weird. The Milky Way galaxy weighs about 1.5 trillion times more than the Sun. But when you add up all the stars, all the gas clouds, all the planets, everything we can actually see, you only get about 200 billion solar masses. So where's the rest? It's dark matter. Invisible stuff that doesn't interact with light at all. We can't see it, can't touch it, can't detect it directly. We only know it exists because of gravity. Galaxies rotate too fast to hold together based on their visible mass. There must be something else, something invisible, providing the extra gravity to keep everything from flying apart. About 85% of the matter in the galaxy is dark matter. We're swimming in it. Dark matter particles might be passing through your body right now, billions of them every second, and you'd never know. We have no idea what it is. It's not atoms, it's not black holes. It's something else entirely, something that makes up most of the mass of the universe, and we can't detect it except through its gravitational effects. This is humbling. We've figured out atoms, quantum mechanics, relativity. We've sent probes to the edge of the solar system and split apart the building blocks of matter. And yet, 85% of the stuff in the galaxy is completely mysterious to us. One more thing before we zoom out again. Let's talk about time scales. We think of the galaxy as eternal and unchanging, but it's not. It's alive with activity, just on timescales so long that human lifetimes can't perceive it. Stars are born in massive clouds of gas and dust. These nurseries, like the Eagle Nebula's pillars of creation, are light years across. Over millions of years, gravity slowly compresses the gas until it ignites in nuclear fusion. A new star is born. That star lives for millions or billions of years, depending on its mass. Small red dwarfs burn for trillions of years. Massive blue giants burn fast and die young, exploding as supernovae after just a few million years. When stars die, they return their material to the galaxy. The carbon in your body, the oxygen you breathe, the iron in your blood, all of it was forged inside stars that exploded billions of years ago. You are literally made of stardust. The galaxy recycles itself. Gas becomes stars, stars explode. Gas becomes new stars, enriched with heavier elements, and the cycle continues. Our sun is a third or fourth generation star. It formed from the remnants of earlier stars that lived and died before our solar system even existed. In about 5 billion years, the sun will run out of hydrogen fuel, swell into a red giant, and eventually shed its outer layers, creating a beautiful planetary nebula. The core will shrink into a white dwarf, slowly cooling over trillions of years. Earth will be long gone by then, either swallowed by the expanding sun or scorched into a lifeless rock. But the atoms that make up Earth and you will still be here, scattered, mixed with gas and dust, waiting to be recycled into new stars and planets. Nothing is permanent. Not stars, not planets, not galaxies. Everything is temporary, even on cosmic scales. But we're getting ahead of ourselves, because as big as the Milky Way is, as impossible as it seems to cross even a tiny fraction of it, we're about to discover that our galaxy is just one grain of sand on an infinite beach. Let's zoom out. Every star you've ever seen with your naked eye is in the Milky Way. Every single one. All those thousands of points of light scattered across a dark sky, they're all our neighbors, relatively speaking. Except for three. 3 fuzzy patches visible from Earth without a telescope are actually other galaxies. The Andromeda Galaxy, visible from the northern hemisphere, and the large and small Magellanic Clouds, visible from the southern hemisphere. Andromeda is 2.5 million light-years away. The light you see from Andromeda left that galaxy when early humans were first learning to make stone tools.
When that light began its journey, Homo sapiens didn't exist yet. And Andromeda is our closest large galactic neighbor. Think about that. The nearest major galaxy is 2.5 million light-years away. That's 15 quintillion miles. If you could travel at the speed of light, it would take 2.5 million years to get there. But here's the beautiful and terrifying part. Andromeda is coming toward us. It's approaching at 68 miles per second. In about 4.5 billion years, the Andromeda galaxy and the Milky Way will collide. Don't panic. Galaxies are mostly empty space, remember? When they collide, the stars won't actually hit each other. They'll pass through like two swarms of bees flying through each other. But the gravitational chaos will fling stars in random directions. Our solar system might get thrown out into intergalactic space, becoming a rogue system drifting alone in the void. Or we might get pulled toward the merged galactic center. Either way, the night sky will look completely different. Andromeda will fill half the sky, a swirling mass of billions of stars. Then, over millions of years, the two galaxies will merge into one enormous elliptical galaxy that astronomers have already named Milky Way. But humans won't be around to see it. The sun will have already destroyed Earth by then. The Milky Way and Andromeda aren't alone. We're part of a small cluster called the Local Group, containing about 80 galaxies spread across 10 million light-years of space. Most of these galaxies are tiny, dwarf galaxies with just a few billion stars, orbiting the Milky Way and Andromeda like moons around planets. The Magellanic Clouds are examples of these dwarf galaxies, slowly being torn apart by the Milky Way's gravity. The entire local group is bound together by gravity. We're all falling toward each other in slow motion, orbiting a common center of mass somewhere between the Milky Way and Andromeda. 10 million light-years. That's the size of our cosmic village. It contains maybe 1 trillion stars total, and it's a tiny, insignificant speck in the larger universe. Zoom out further, and you discover that the local group is just one neighborhood in a much larger structure called the Virgo supercluster. The Virgo supercluster contains over 100,000 galaxies spread across 110 million light-years of space. At its heart sits the Virgo cluster, a dense collection of over 1,300 galaxies. Some of these galaxies are giants, each containing trillions of stars. One galaxy in the Virgo cluster, called M87, has a supermassive black hole at its center weighing 6.5 billion times more than the Sun. This is the black hole that scientists photographed in 2019, creating that famous image of a glowing orange ring around a dark center. That dark center is the event horizon, the point of no return where even light can't escape. The jet shooting out of M87's black hole stretches for 5,000 light-years. That's a beam of superheated plasma longer than the distance between Earth and our nearest star, being shot out at nearly the speed of light. This jet has been active for millions of years, pumping energy into intergalactic space. The Virgo supercluster weighs about 1 quadrillion times more than the Sun. That's 1,000 trillion, a 1 followed by 15 zeros. And the entire thing, all 100,000 galaxies, is slowly collapsing toward its center. Gravity is pulling everything together. Over hundreds of billions of years, the galaxies in the supercluster will merge into one enormous galaxy, alone in the darkness. But that's not going to happen, because of something much stranger. In the 1970s, astronomers discovered something bizarre. Our entire supercluster is moving, not just expanding with the universe, but actually moving towards something. They called it the Great Attractor. It sits about 150 million light-years away, hidden behind the plane of the Milky Way, so we can't see it directly. But we can measure its gravitational effect. Tens of thousands of galaxies are streaming toward it at 600 kilometers per second. For decades, we didn't know what the Great Attractor was. Then, as telescope technology improved, we discovered it's not a single thing. It's a region of space with an unusually high density of matter, a gravitational anomaly pulling everything nearby toward it. But then we discovered something even bigger. In 2014, astronomers mapped the movement of galaxies across a huge volume of space. They tracked which direction galaxies were moving and how fast, and they discovered that our supercluster is part of something much bigger. They called it Laniake, a Hawaiian word meaning immeasurable heaven. Laniake is a supercluster of superclusters, containing over 100,000 galaxies spread across 520 million light-years. Everything in Laniake is flowing toward the same gravitational center, like rivers flowing toward an ocean. The mass of Laniake is estimated at 100 million billion times the mass of the Sun. That number is so large, it's meaningless. There's no way to visualize it or comprehend it. And Laniake isn't the largest structure we've discovered. There are bigger superclusters out there. The Shapley supercluster contains over 8,000 galaxies. The Hercules Corona Borealis Great Wall stretches across 10 billion light-years, making it the largest known structure in the universe. At this scale, galaxies become pixels. Clusters of galaxies become dots. The universe reveals itself not as a collection of objects, but as a web.
Map enough galaxies, and a pattern emerges. Galaxies aren't randomly scattered through space. They're organized into a vast cosmic web of filaments and sheets, with enormous voids in between. These filaments are made of dark matter, with galaxies strung along them like lights on a web. The filaments connect at nodes where massive galaxy clusters form. And between the filaments are voids, vast, empty regions hundreds of millions of light-years across, containing almost no galaxies at all. This is the largest scale structure in the universe, the cosmic web. It formed in the early universe when matter began clumping together under gravity. Dark matter collapsed first, forming the scaffolding. Then, normal matter followed, falling into the dark matter gravitational wells and forming galaxies. If you could see dark matter, the universe would look like a three-dimensional spider web with glowing galaxies marking the strands. The voids are the emptiest places in existence. Inside a void, you'd see almost no galaxies in any direction. The universe would look empty, dark, and cold. If an intelligent civilization evolved in a galaxy inside a void, they might never discover that other galaxies exist. They'd think their galaxy was the entire universe. We're lucky. We're in a densely populated region of space, surrounded by neighbors. We can see the universe in all its glory. Now we're ready for the big zoom out, the ultimate view. The observable universe is a sphere centered on Earth, with a radius of about 46.5 billion light-years. That gives it a total diameter of 93 billion light-years. Wait, you might be thinking, if the universe is only 13.8 billion years old, how can the observable universe be 93 billion light-years across? Shouldn't it be 27.6 billion light-years, accounting for light traveling in both directions? This is where the expansion of space comes in. The universe isn't static, it's expanding. Space itself is stretching, carrying galaxies apart from each other. A galaxy that emitted light 13 billion years ago was much closer to us back then, but in the time it took that light to reach us, the expansion of space carried that galaxy much further away. So today, that galaxy is now 46 billion light-years away. Even though we're seeing light, it emitted when it was much closer. This is one of the most brain-breaking concepts in cosmology. Space itself is expanding. Not expanding into anything, just expanding. The distances between things are increasing not because things are moving through space, but because space itself is getting bigger. Within this observable universe, astronomers estimate there are about 2 trillion galaxies. That's 2 trillion galaxies. Most of them are small dwarf galaxies, but even if we assume an average of just 100 billion stars per galaxy, that's 200 billion trillion stars. Written out, 200 billion trillion stars. And each of those stars could have planets. Maybe half of them do on average. That's 100 billion trillion planets. And maybe 1% of those are in the habitable zone where liquid water could exist. That's still a billion trillion potentially habitable planets. The odds that we're alone become vanishingly small. But here's the thing. The observable universe is not the whole universe. It's just the part we can see. Light from more distant regions hasn't had time to reach us yet. And because the universe is expanding, there are regions of space that are receding from us faster than light can travel. Light from those regions will never reach us. This creates a cosmic horizon, like the horizon on Earth where the curvature of the planet blocks your view. Beyond our cosmic horizon, there are galaxies we will never see, stars that will never be visible from Earth, entire superclusters forever hidden from us. And as the universe continues to expand, this horizon is actually getting closer. Galaxies that we can see today will eventually cross the horizon and disappear from view forever. In the far future, trillions of years from now, intelligent beings in our galaxy will look out and see almost nothing. A few nearby galaxies, and beyond that, darkness. They'll have no way to know that the universe was once full of billions of galaxies. The evidence will be gone, carried away by the expansion of space. We're living in a golden age of astronomy. We can see the universe. Future civilizations won't be so lucky. So how big is the universe? The observable universe is 93 billion light-years across. That's the sphere of space from which light has had time to reach us. But the actual universe? We don't know. It could be slightly larger than the observable universe. It could be thousands of times larger. It could be infinite. Current evidence suggests it's probably much larger than what we can see, possibly infinite. The cosmic microwave background, the afterglow of the Big Bang, shows that the universe is very flat on large scales. And in most models of cosmology, a flat universe is an infinite universe. But we can't know for sure. We can only see 93 billion light-years in any direction. Beyond that is mystery. We're about to tackle the second question. Does the universe end? And the answer is going to get even weirder.
Does the universe end? It's such a simple question, and yet it might be the hardest question humans have ever asked, because every possible answer breaks our brains in a different way. Let's start with the possibilities. Maybe the universe just goes on forever. Infinite space, infinite galaxies, infinite stars, infinite planets. No edge, no boundary, no end. Just more and more and more forever. This seems impossible to imagine. How can something have no end? Our experience tells us everything has boundaries. Rooms have walls. Countries have borders. Even the ocean has coastlines. Here's an analogy. Imagine you're an ant living on a balloon. From your perspective, the surface of the balloon is your entire universe. Now, someone starts blowing up the balloon. The surface expands. The distance between any 2 points on the balloon increases. But does the surface have an edge? No. You could walk forever in any direction and never reach a boundary. The surface is finite in area, but it has no edge. It curves back on itself. Now extend this to 3 dimensions. Our universe might be like that. Finite in volume, but with no edges, because it curves back on itself in a way we can't visualize. Or it might actually be infinite, truly endless, in which case, somewhere out there, impossibly far away, there's another version of Earth, another you. Because in an infinite universe with infinite matter, every possible arrangement of atoms must occur eventually, including an exact copy of you.
In fact, in a truly infinite universe, there are infinite copies of you. Some slightly different, some identical. Infinite versions of Earth, infinite versions of human history. This is the concept of the Level 1 multiverse, proposed by physicist Max Tegmark. If space goes on forever, and matter is distributed roughly uniformly, then everything that can happen must happen somewhere, including exact duplicates of our observable universe. The math suggests your nearest identical copy is about 10 to the power of 10 to the 29 meters away. That's a 1 followed by 10 billion billion digits. A distance so large that writing it down would take more atoms than exist in the observable universe. Maybe the universe does have an edge, but you can never get there because space is expanding faster than you can travel. Remember, distant galaxies are receding from us faster than light. Not because they're moving through space that fast, but because space between us and them is expanding. The further away a galaxy is, the faster it appears to recede. There's a distance, called the cosmic event horizon, beyond which galaxies are receding faster than light. We can never reach those galaxies, even if we traveled at light speed forever, because the space between us and them is stretching faster than we can cross it. So maybe the universe does have an edge beyond that horizon, but we can never reach it, never see it, never know it's there. Maybe the universe just stops. You travel far enough and suddenly there's a boundary, a wall, an edge, and beyond it, nothing. Not darkness, not empty space, nothing. No space, no time, no dimensions at all. True nothingness. But this creates immediate problems. What does an edge look like? Can you touch it? If you throw a ball at it, does it bounce back? Does it disappear? These questions don't make sense because our brains can't process nothing. We always think of space as a container, a box that things exist inside. But space isn't a container. It's part of the universe itself. Asking what's outside the universe is like asking what's north of the North Pole. The question doesn't make sense because direction is defined by the Earth's surface, and at the North Pole, there is no further north. Similarly, outside is a spatial concept. It only makes sense within space. If the universe is all of space, then outside the universe is a meaningless phrase. Maybe the universe doesn't have an edge because it curves back on itself in time as well as space. This is the Big Bounce theory, the idea that the universe expands, reaches a maximum size, then contracts back down in a big crunch. All matter collapses back to a point, then explodes again in a new Big Bang. The cycle repeats forever. In this model, the universe is finite in space and time, but it has no beginning and no end. It's been bouncing forever, each cycle potentially with different laws of physics, different constants, different structures. We might be living in cycle number infinity. Before our Big Bang was a big crunch. Before that was another expanding universe with its own galaxies, stars, and perhaps civilizations. All of it crushed down to a point and recycled into our universe. But current observations don't support this. The universe is expanding, and the expansion is accelerating. There's no sign it will ever contract. Unless something changes, our universe will expand forever, growing colder and darker until it reaches heat death. In 1998, astronomers made a discovery that shocked the scientific world. The expansion of the universe is speeding up. This shouldn't be possible. Gravity should be slowing the expansion down. All the matter in the universe pulling back, trying to collapse everything together. The expansion should be decelerating. But it's not. It's accelerating. Something is pushing space apart, overpowering gravity. They called this something dark energy, and we have no idea what it is. Dark energy makes up about 68% of the universe. Dark matter makes up another 27%. Everything we can see, all the stars and galaxies, all the planets and gas clouds, all the stuff we think of as the universe, is only 5% of what's actually out there. We're living in a universe where 95% of the content is completely mysterious to us. Dark energy is stranger than dark matter because it's not stuff, it's a property of space itself. Every cubic meter of space contains a tiny amount of dark energy, and as space expands, creating more cubic meters, there's more dark energy. This creates a feedback loop. More space means more dark energy. More dark energy means faster expansion. Faster expansion creates more space. If dark energy continues to accelerate the expansion, the universe will end in what's called the Big Rip. In about 22 billion years, the expansion will become so fast that it tears galaxies apart, then solar systems, then planets, then molecules, then atoms, then even subatomic particles will be ripped apart. Space itself will be shredded. Or maybe dark energy will weaken over time, and the universe will coast to a gentler end, slowly fading into darkness over trillions of years. We don't know. We can't predict it because we don't know what dark energy is. But wait, there's an even more mind-bending possibility. Maybe our universe isn't the only one. Multiverse theories come in several flavors, each more bizarre than the last. The level 1 multiverse is what we talked about earlier. If space is infinite, there are infinite copies of everything, including you. The level 2 multiverse comes from eternal inflation theory. In this model, our Big Bang wasn't a one-time event. It's happening everywhere, all the time. Space is constantly spawning new bubble universes, each with its own Big Bang. These bubble universes are separated by regions of eternally inflating space. They can never interact or communicate. Each bubble might have different laws of physics, different numbers of dimensions, different values for fundamental constants. Some bubbles might have no stars, some might have no atoms, some might be filled with life. We live in one bubble, a bubble with 3 dimensions of space, 1 of time, and physical constants perfectly tuned to allow galaxies, stars, planets, and life. Not because we're special, but because we could only exist in a bubble with these properties. It's a selection effect. We observe this type of universe because this is the only type where observers can exist. The level 3 multiverse comes from quantum mechanics. Every time a quantum measurement is made, the universe splits into multiple versions, one for each possible outcome. There's a universe where you sneezed just now, another where you didn't. A universe where dinosaurs never went extinct. A universe where you made every opposite choice you've ever made. These parallel universes all exist simultaneously, branching endlessly, creating an infinite tree of possibilities. And the level 4 multiverse is the most abstract. It's the idea that all possible mathematical structures exist as physical realities. Every universe that can be described by mathematics actually exists somewhere. Our universe, with its particular laws of physics, is just one mathematical structure among infinite others. In this view, the question, why does the universe obey these particular laws, is answered by, all laws exist in different universes. We're in this one because we can only exist in the universe with these laws. And then there's the simulation hypothesis. Maybe we're not in a physical universe at all. Maybe we're in a computer simulation created by some advanced civilization. The universe is just code running on some unimaginable hardware. In this case, the universe doesn't need to be infinite. It only needs to simulate what we observe. The far edges of the universe might not even be rendered yet, like a video game that only loads terrain when the player gets close. This sounds like science fiction, but some physicists take it seriously. Here's why. If it's possible to create simulated universes that are convincing enough that the simulated beings think they're real, then advanced civilizations will probably create many such simulations. For every one real universe, there could be millions or billions of simulated ones. So, statistically, if simulated universes are possible, we're probably in one. You can't disprove this idea. Any evidence we gather about the universe could just be part of the simulation. The laws of physics could be the rules of the program. Quantum mechanics could be the simulation's way of saving computational resources by not rendering things until they're observed. It's unfalsifiable, which makes it unscientific, but it's also not disprovable. Here's a key insight that ties many of these ideas together: the anthropic principle. The universe appears fine-tuned for life. The constants of physics are set to very precise values. If the strong nuclear force were slightly weaker, atoms couldn't form. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If the cosmological constant were much larger, the universe would have expanded too fast for galaxies to form. Change any of these constants by tiny amounts, and you get a sterile universe with no complexity, no structure, no life. So why is our universe so perfectly tuned? The anthropic principle says, we observe a life-friendly universe because we couldn't exist in any other kind. It's a selection effect. Not because the universe was designed for us, but because we can only observe universes compatible with our existence. If there's only one universe, this is a troubling coincidence. But if there are infinite universes with different properties, then it makes perfect sense. Most universes are dead and sterile. We happen to be in one of the rare ones that allows observers to exist. We're not special. We're just lucky. So, does the universe end? Honestly, we don't know. The observable universe is 93 billion light-years across. Beyond that, we can't see. We can't measure. We can only theorize. The universe might be infinite. It might be finite but unbounded. It might be one of infinitely many. It might be a simulation. It might end in fire. It might end in ice. It might end when someone unplugs the computer. Every answer we come up with raises new questions. Every solution creates new mysteries. But here's what we do know. The universe is vastly, incomprehensibly larger than anything our ancestors imagined. We've gone from thinking Earth was the center of everything to realizing we're a speck on a speck, orbiting a speck in a collection of specks that's itself just one speck among countless others. And yet, we figured this out. Tiny creatures on a tiny planet used math, telescopes, and curiosity to map the cosmos. We measured distances our ancestors couldn't even conceive of. We discovered galaxies, black holes, dark matter, dark energy, the cosmic web. We might be small, but we're not insignificant, because we're the part of the universe that wakes up and tries to understand itself. Learning about the true scale of the universe changes you. It has to. You realize that everything you worry about, everything you think is important, happens on a scale so small it's invisible from even the nearest star. Your entire life, everyone you'll ever meet, every human who has ever lived, we're all confined to one tiny rock in an endless ocean of space. This could be depressing. It could make everything feel meaningless. Or it could be liberating. Because if we're this small, then our mistakes aren't that big either. The things you regret, the embarrassing moments that keep you awake at night, the failures that feel crushing, from a cosmic perspective, they don't matter at all. But the things you love, the people you care about, the moments of beauty and connection and joy, those matter because you decide they matter. The universe doesn't care, but you do, and that's enough. We live in a golden age. We're the first generation of humans to truly understand our place in the cosmos. Ancient people thought Earth was flat and the stars were lights on a dome. Medieval people thought Earth was the center of a small universe. We know better. We've measured the distances. We've seen the galaxies. We've mapped the cosmic web. And we're the last generation who will be able to see the full glory of the universe. Because as the universe expands, galaxies will disappear beyond the cosmic horizon. In 1 trillion years, all the distant galaxies will be gone, redshifted into invisibility. Future civilizations will look out at a dark, empty sky and think they're alone. But we're here now. We can see it all. We're living in the brief window when the universe is old enough to be interesting, but young enough to still be observable. That's incredible. That's a gift. So, how big is the universe? Bigger than you can imagine. Probably infinite. Definitely larger than we can ever explore. Does it end? Maybe. Probably not. We'll never know for sure. But the search for answers, the journey to understand, that's what makes us human. We're explorers by nature. We look at the horizon and wonder what's beyond it. We always have, we always will. The universe gave us curiosity. It made us smart enough to ask questions, but limited enough that we'll never run out of mysteries to solve. And maybe that's perfect. Maybe the journey is the point. Not the destination, but the endless pursuit of knowledge, the constant pushing against the boundaries of the unknown. So keep looking up. Keep asking questions. Keep wondering. Because somewhere out there, in the vast darkness between the stars, are answers we haven't even thought to look for yet. The universe is waiting, and we've only just begun to explore it.
We've talked about the impossibly large. Now let's talk about the impossibly small. Because the universe gets just as weird when you zoom in as when you zoom out. There's a limit to how small distances can be. It's called the Planck length, and it's about 1.6 times 10 to the minus 35 meters. That's a decimal point followed by 34 zeros and then a 1.6. To put this in perspective, the Planck length is to an atom what an atom is to 100 trillion kilometers. It's the smallest meaningful distance in physics. Below the Planck length, space and time themselves become quantum. They stop being smooth and continuous and start bubbling and fluctuating. At this scale, tiny black holes might constantly pop in and out of existence. Time might not flow forward consistently. Cause and effect might break down. We call this quantum foam. It's the texture of space-time at its most fundamental level. And we have absolutely no way to study it directly. No microscope will ever see the Planck scale. The energy required to probe distances that small would create a black hole that would immediately collapse. Here's the kicker. If our universe is a simulation, the Planck length might be the pixel size, the resolution of reality itself. Below that, nothing is rendered because nothing needs to be. Black holes destroy information. At least they seem to. When something falls into a black hole, all information about what it was made of, its quantum state, everything that made it unique appears to be lost forever. The black hole just gets slightly heavier, and that's it. But quantum mechanics says information can never be destroyed. It can be scrambled, hidden, transformed, but not deleted from existence. This is a fundamental law as important as conservation of energy. So we have a paradox. Black holes seem to destroy information, but information can't be destroyed. Something has to give. Stephen Hawking spent decades working on this. He initially argued that information really is destroyed, which would mean quantum mechanics is wrong. Later, he changed his mind and proposed that information might be encoded on the black hole's event horizon, the boundary of no return. This led to the holographic principle, the idea that all the information in a volume of space can be encoded on its boundary, like a hologram, a 3D image stored on a 2D surface. Some physicists now think our entire universe might be a hologram, that what we experience as three-dimensional space is actually information encoded on a distant two-dimensional surface. We're living in a projection.
This isn't metaphor, this is serious physics being studied by top researchers at places like Princeton and Stanford. If true, it means the universe isn't what it seems. Reality itself might be an illusion, a shadow cast by some deeper structure we can't perceive directly. Quantum mechanics tells us that particles don't have definite properties until they're measured. Before measurement, an electron doesn't have a specific location. It exists in a superposition of all possible locations simultaneously. The act of measurement forces the particle to choose a specific state. The wave function collapses, and reality crystallizes into one particular outcome. But what counts as a measurement? Does it require a conscious observer, or does any physical interaction enough? This is the measurement problem, and it's been argued about for a century. Some physicists think consciousness plays a role, that the universe exists in a hazy, undefined state until someone looks at it. This would mean observers literally create reality through observation. Others think that's absurd. They argue that measurement is just any physical interaction, and consciousness has nothing to do with it. Others, subscribing to the many worlds interpretation, think there is no collapse. Every possible outcome happens in a different branch of the quantum multiverse. You might have chosen to watch this video in this timeline, but there's another timeline where you clicked away, another where you never found the video at all, another where YouTube was never invented, another where humans never evolved. All of them equally real, equally happening, just in different branches of the quantum multiverse. This isn't settled science. This is ongoing debate among the smartest physicists alive. We still don't know how reality works at its most fundamental level. There's a number that appears throughout physics, 1/137.036. It's called the fine structure constant, and nobody knows why it has this value. It determines the strength of electromagnetic interactions. It shows up in equations describing atoms, light, quantum field theory, basically everywhere. If this number were even slightly different, chemistry wouldn't work, atoms wouldn't form properly, stars couldn't create the elements needed for life. Physicist Richard Feynman called it one of the greatest damn mysteries of physics. He said every good theoretical physicist should worry about this number, because it's not derived from anything else. It's not calculated from deeper principles. It just is. The universe comes with this number built in, and we have no idea why. Some physicists think it might change over time, that the fine structure constant might have been different in the early universe. There's weak evidence for this in observations of distant quasars, but it's controversial. If true, it would mean the laws of physics themselves evolve, that the universe we see today operates differently than it did 13 billion years ago. Here's a thought experiment that will haunt you. In an infinite universe, or given infinite time, random quantum fluctuations will eventually create any configuration of matter, no matter how unlikely, including a brain. A fully formed brain with memories and thoughts spontaneously popping into existence from random chance. This is called a Boltzmann brain, named after physicist Boltzmann.
Here's the problem. It's far more likely for a single brain to randomly appear than for an entire universe with consistent laws of physics to evolve naturally. Statistically, Boltzmann brains should vastly outnumber real brains in evolved bodies, which means if you pick a random conscious observer in the universe, it's probably a Boltzmann brain that just flickered into existence and will disappear in the next instant. And it gets worse. A Boltzmann brain could have false memories. It could remember a life that never happened. It could be convinced it's you, right now, reading this sentence, even though it just spontaneously formed 1 second ago and will disintegrate in the next second. You can't prove you're not a Boltzmann brain.
Any evidence you appeal to could be a false memory implanted by random chance. This is called the Boltzmann brain paradox, and physicists hate it because it undermines our ability to trust any observation about the universe. If most observers are Boltzmann brains with false memories, then our scientific understanding of reality might be completely wrong. The only way out is to argue that the universe isn't infinite, or that it will eventually reach a state where random fluctuations can't create complex structures anymore. But both of these require assumptions about cosmology that we can't verify. Let's return to the alien question, but deeper this time. The galaxy is 13.6 billion years old. Our sun is only 4.6 billion years old. That means there were billions of years before our solar system even existed for other civilizations to emerge. If even one intelligent species arose just 1 million years before us, and if they developed interstellar travel, they could have colonized the entire galaxy by now. Even traveling at a small fraction of light speed, 1 million years is enough time to spread everywhere. So where are they? Maybe intelligence is incredibly rare. Maybe we're the first. But statistically, that seems unlikely. Maybe civilizations destroy themselves before they can colonize the galaxy. Nuclear war, climate catastrophe, artificial intelligence gone wrong, engineered pandemics. There might be a great filter, some inevitable catastrophe that wipes out every species before they can spread to the stars. Maybe the filter is behind us. Maybe the hard step is going from single cells to complex life, and we've already passed it. In that case, we're safe. Or maybe the filter is ahead of us. Maybe something kills every civilization that reaches our level, and we're about to find out what it is. Or maybe aliens are already here and we just can't recognize them. Maybe they exist at scales or in forms so different from us that we're like ants trying to understand the internet. Maybe they're watching us right now and we're too primitive to notice. Or maybe, and this is the loneliest possibility, space is just too big. Maybe there are millions of civilizations out there, but the distances are so vast that we'll never meet. Each species alone on their island, shouting into the void, never hearing a response. We might be surrounded by neighbors and never know it. Let's talk about the far future, the deep future. Trillions of years from now. Stars will eventually burn out. All of them. Every star in the galaxy will exhaust its fuel and fade. Red dwarfs can last for 10 trillion years, but even they will eventually die. In 100 trillion years, the last stars will flicker out. The universe will go dark. But things will still happen, just slower. Black holes will evaporate through Hawking radiation. This process takes an unimaginably long time. A black hole with the mass of the sun would take 10 to the 67 years to evaporate completely. That's a 1 followed by 67 zeros. The supermassive black holes at the centers of galaxies will last even longer, 10 to 100 years or more. After the black holes evaporate, all that's left is a thin soup of photons and elementary particles spread across an ever-expanding universe. The temperature approaches absolute zero. Nothing interesting can happen anymore. No stars, no planets, no life, no structure. This is called heat death. The universe reaches maximum entropy, a state of total equilibrium where no energy flows and no work can be done. But even this isn't the end. After 10 to the power of 10 to the power of 56, quantum tunneling might cause all matter to spontaneously transform into iron, the most stable element. Then the iron itself might decay. Eventually, given enough time, anything that can happen will happen. Random quantum fluctuations might create new big bangs. New universes could bubble into existence from the void. Time loses all meaning in this era. Nothing changes, nothing happens, and yet time continues, possibly forever. Some physicists speculate that conscious observers might still exist even then. Advanced civilizations might survive by slowing down their thought processes, thinking one thought every trillion years. existing in a state of suspended animation, occasionally waking up to think a single thought before going dormant again. They would experience subjective time normally, but from an outside perspective, they'd be thinking in extreme slow motion, making each thought last as long as possible to conserve the dwindling energy reserves of the dying universe. This is called the slow thinking scenario, and it's one of the only ways life might persist into the deep future.
If we are in a simulation, when does it end? Maybe it runs forever. Maybe whoever created it is curious to see what happens. Or maybe it runs until we figure out we're in a simulation. That could be the exit condition. Once the simulated beings become self-aware enough to question their reality, the simulation ends. In which case, this video might be dangerous. By spreading awareness of the simulation hypothesis, we might be triggering the shutdown condition. Or maybe the simulation ends when we reach a certain level of technological development. Maybe the point of the simulation is to see if we can solve certain problems. Climate change, nuclear weapons, artificial intelligence. Once we either solve them or destroy ourselves trying, the simulation completes and the results are recorded. Or maybe it's already ended. Maybe you're experiencing the last few seconds of the simulation right now, and everything you remember about your life before this moment is false memory, implanted data to give context to these final moments. You can't disprove this. Any evidence you think of is itself part of the simulation. This is the epistemic nightmare at the heart of the simulation hypothesis. If it's true, we can't trust anything. All of science, all of our observations could be artificial. Most physicists dismiss this as unfalsifiable and therefore unscientific, but that doesn't make it false. It just makes it untestable. Physicist Frank Tipler proposed something called the omega point theory. It's wild, speculative, and probably wrong, but it's fascinating. The idea is that as the universe approaches its end, intelligent life will have colonized everything. Civilizations will have merged into a single cosmic intelligence, a godlike entity with access to all the matter and energy in the universe. As space contracts in the final moments before a big crunch, if that happens, this superintelligence will use the energy of the collapse to perform infinite computations. Time will slow down from its perspective, allowing it to think infinite thoughts in finite time. In its final moments, this cosmic mind will simulate every possible universe, every possible life, every possible experience. It will become omniscient and omnipresent. And if we're patterns of information, then being simulated is the same as existing, which means all of us, everyone who has ever lived, will be resurrected in the final computation. Will live again in the mind of this cosmic God. This is Tipler's omega point. It's physics as theology. Most scientists think it's nonsense, but it's an interesting idea, that consciousness is the ultimate destiny of the universe and that the purpose of all existence is to give rise to a final, infinite mind. Here's my honest take. And I say this after researching this topic for months, reading hundreds of papers, talking to physicists, lying awake at night staring at the ceiling. We don't know anything. Not really. We have models. We have equations that predict observations. We have theories that work within certain domains. But we don't understand reality. We don't know what dark matter is. We don't know what dark energy is. That's 95% of the universe. That's a complete mystery. We don't know why quantum mechanics works. We don't know what causes wave function collapse, or if it even happens. We don't know if there are other universes. We don't know if our universe is infinite. We don't know why the constants of physics have the values they do. We don't know what came before the Big Bang. We don't know if time is fundamental or emergent. We've made incredible progress.
We've mapped the cosmos, split the atom, sequenced the genome, built computers. We've done things our ancestors would call magic. But at the deepest level, we're still confused children trying to make sense of a reality far stranger than we have the capacity to understand. Maybe that's okay. Maybe the point isn't to understand everything. Maybe the point is the journey, the endless questioning, the constant discovery, the perpetual wonder. We're the universe asking questions about itself, and maybe that's enough. You made it. You watched over an hour of content about the scale of the universe, the nature of reality, and questions we may never answer. That says something about you. You're curious. You're willing to sit with uncomfortable ideas. You want to understand even when understanding feels impossible. The universe is bigger than we can imagine, stranger than we can conceive, more mysterious than we have words to describe. And you're part of it. Every atom in your body was forged in the heart of a dying star. You're made of stardust, animated stardust, stardust that woke up and learned to ask questions. That's not nothing. That's actually incredible. So keep asking questions. Keep looking up. Keep wondering. Because even though we're tiny, even though we'll never fully understand, the fact that we try means something. It means we're alive. It means we're conscious. It means we're here, now, in this brief window of time when the universe is old enough to be interesting, but young enough to still be observable. That's a gift. Don't waste it. The universe is waiting, and so are the answers we haven't found yet. Thanks for watching. Now, go outside, look up at the stars, and remember, you're not looking at the universe. You're part of it, looking at itself. And that changes everything.